Okay, let us continue with the description of a system. Let's expand upon what we have done in the last section regarding mass and mole. So we have a system in equilibrium. Let's put it, anything inside a boundary is called a system, recall that. And let's assume the system is in equilibrium and it's uniform. So you have a uniform system. That means everywhere in the system the properties are same. There is no difference between locations. And because it's in equilibrium, nothing is changing with time either. We have already encountered the amount of the system, mkg or n kilomole. We have also talked about already the stored energy E to be Ke plus Pe plus Eu. Note that we use capital letters to describe total properties. So these are total system properties. Each of them has a unit of kilojoule. Obviously, since the system is uniform, we could also express specific properties. We'll define E to be capital E over m, which is the unit becomes kilojoules per kg. So what would be the definition of E? E would be capital E over m, and if I divide each quantity in this expression by m, it becomes Ke over m, Pe over m plus U over m. And our convention will be specific properties will use lowercase letter. So instead of writing Ke over m all the time, we'll write small ke, small pe, and small eu. So using this stored energy, we want to show you we want to establish a pattern here. So these are called specific properties. So each of them will be what? Specific kinetic energy, specific potential energy, or specific internal energy. So it's very easy to go back and forth between total and specific properties. So what is capital E? Is simply m times E. What is capital kinetic energy? Is m times small ke. This is total kinetic energy, and this is specific kinetic energy. Similarly, Pe equals m times Pe, and Eu equals m times Eu. So what would be a formula for instance, if somebody says, what is the formula for small ke? Well, we know capital Ke is mv square over 2000 in kilojoule. Instead of half mv square, we use 2000, remember? Recall that to have the unit of kilojoule, which is a more convenient unit. So therefore, what is K? Small ke is capital Ke divided by mass. So it simply becomes v squared by 2000 kilojoule per kg. Similarly, small pe will be gz over 1000. So notice already we have quite a few properties that we have come across: pressure, temperature, mass, volume of the system. Everybody knows what is density, of course. We also define specific volume as 1 over density, if you recall. Again, let me formally define. Specific volume is defined as volume per unit mass, meter cube over kg. So PT, mv, rho, v, and then we have come across EU, capital EU, small ke, capital Ke, small pe, capital Pe, small e, capital E. So notice the set of properties that we are describing the system with is expanding. We have a whole lot of properties already. Before we develop a classification method, let's talk about a few other properties. Actually, one of the most important properties. We'll just go one quick round about that property, And we'll talk about it more and more, and it's called the property of entropy. We'll spend quite some time on this property in the coming chapters. But at this point, I just want to establish the basic stuff. The symbol used is capital S. It's called entropy. The unit is kilojoule. Right now, the unit really doesn't matter. Later on, you will see why it's such an unit. And like mass, like volume, entropy also can be specific entropy expressed per unit mass, which is small s, capital S divided by m. I'm sorry, here the unit is kilojoule per Kelvin, and specific entropy is kilojoule per kgk. So see how you can catch your mistake. The lowercase letter will always have per kg, and uppercase letter will not have, uppercase symbol will not have per kg. So it's all about just symbols. So what really is entropy? Go back for a moment, what is energy? If you recall, energy is, if I go for specific energy, Ke plus Pe plus Eu. Ke and Pe are connected with organized position or motion of molecules, right? Suppose a baseball is traveling very fast. That means it has a high kinetic energy. All the molecules are moving fast. Pe means all the molecules are at a higher location or elevation. But what is Eu actually? Eu is Ke and Pe of molecules, if you recall our discussions. Eu is the aggregate Ke and Pe of all the random energy of molecules. And these are kind of organized. You can think like organized molecular energy. All the molecules are moving together. And these are like disorganized energy of the molecules. Ultimately, the energy of a system is the energy of its molecules. And I'm just dividing them into two classes. Organized means all the molecules of a baseball are moving with the speed of the baseball. That's the organized motion of all the molecules. Versus when a copper block is very hot, we know it is reflected in higher kinetic energy of the molecules. When you touch it, the molecules are vibrating so fast, it will hit your neurons, and that's how you feel the degree of hotness of a copper block. Similarly, a potential energy of molecules can be felt when there's a phase change. Suppose ice becomes a liquid. At that time, what happens? The molecules, essentially the springs which connects the molecules, are elongated much. So the potential energy, which is always arises whenever there's a force field connecting molecules or connecting systems. So even this potential energy, the gravitational potential energy, is the, recall our discussion about an invisible gravitational spring that is pulling every object. And that's what is causing the potential energy, the potential for it to convert its energy into the destructive kinetic energy. So at the molecular level, the same discussion of Ke versus Pe holds. So let's think of just Eu for the time being. So suppose I have a system, so how is the internal energy stored? Well, the internal energy is the sum of all the random energy of the molecules. But how is the energy in a molecule stored? The quantum mechanics tells us that a molecule can have discrete amount of energy level. In other words, it cannot have continuous energy. Well, if you think about it, discrete levels of energy, what it means is kind of totally counterintuitive. It's like somebody saying you can drive at 5 miles per hour, 10 miles per hour, 15 miles per hour. No, nothing else in between. You'll say, in that case, how do I go from 5 to 10 miles per hour? So our sense of continuum is totally lost at molecular levels. So let's stipulate, which is true, it all comes from fundamental laws of nature, that at molecular levels, at very small scale, energy is discretized. So a molecule can have energy levels here or there and there and there. It cannot have a continuous spectrum of energy. Once we accept that, there are a lot of consequences of that. So if we have a certain amount of internal energy, the random energy of molecules in a system, we know from conservation of energy that total energy must remain constant because it cannot be destroyed or created. But the first law doesn't tell us, the energy conservation doesn't tell us anything about how that energy will be distributed. And that's where entropy comes in. Before we get to entropy, let's first figure out in how many ways energy can be stored in a system. Just suppose, for the sake of argument, that we have a system with only 3 molecules. Of course, we understand there are trillions and trillions of molecules. So if each molecule, suppose again for simplicity, each molecule has 5 discrete levels of energy. So in other words, each molecule can have energy only in one of those 5 steps. That it is from your knowledge of permutations, you know, that means energy can be stored in 5 times 5 times 5 equals 125 ways. So if there is a certain amount of energy, the energy can be distributed in 125 ways in this system. And in how many ways the energy can be distributed is connected with entropy. The more number of ways energy can be distributed, a given amount of energy can be distributed, that means the system will have more entropy. So what is entropy? It is defined essentially in how many ways energy can be distributed. But Boltzmann, who defined entropy, defined it in a manner called through logarithm of number of ways in which energy can be distributed. What is omega? This is the number of ways in which energy can be distributed. And he said, let's take a logarithm. Whenever there's a large number, when you take a log of that, it becomes a smaller number. And by the way, k is called the Boltzmann's constant. So why did Boltzmann define entropy in this manner? We know that from fundamental physics, the number of ways in which energy can be distributed becomes important. We'll spend a lot of time on that, why it's important. But why did he bring the law on here in this definition? To understand that, think of 2 systems, 2 identical systems. So each system can store energy in 125 ways. And suppose each system has a mass, of course, they are identical system, 1 kg. Suppose each system has an energy of 100 kilojoules. We immediately recognize that the combined system will have a mass of 2 kg, energy of 200 kilojoules. But in how many ways the energy can be distributed? Of course, we know from your permutation theory, it will be 125 times 125. So look at the genius of Boltzmann by defining entropy as ln of omega. So in other words, if first system has omega 1 ways, omega 2 ways, the combined system we know will have omega 1 times omega 2 ways. But the way logarithm works, the combined entropy, as you can see, will be S1 plus S2 because it is k of ln omega 1 times omega 2, which is k ln omega 1 plus k ln omega 2. In other words, by using logarithm in the definition of entropy, entropy becomes additive just like mass and energy. So to summarize our discussion, entropy is basically the ways is proportional to the number of ways in which internal energy can be distributed amongst molecules in a random ways. So we are first of all excluding the organized energy like kinetic and potential energy of the overall system, and then taking the internal energy and seeing in how many different ways the energy can be stored in the system. It will turn out that the number of ways in which energy can be stored, or entropy, which is the logarithm of that times k, is fundamentally connected to some natural laws. When systems behave in a certain way, we know energy will be conserved. That's called the first law of thermodynamics. We'll discuss that in a later chapter. But also, we'll find some fundamental ways system behaves are connected with entropy. So without going further, let's just stipulate that there's a property, just like energy, mass, there's another property called entropy, which is connected with number of ways in which internal energy of the system can be stored. And the more number of ways the energy can be stored, the more will be the entropy. Well, let's look at some pattern we are already finding. Notice that mass, energy, entropy, volume, these are additive properties, right? Whereas pressure, temperature are not. So all the properties that we are coming across so far, we'll find that they can be divided into two classes. One is called extensive properties, another branch is intensive properties. Extensive means they're additive, like mass, energy, entropy, volume. Intensive could be pressure, temperature, molar mass. Specific energy, look, specific energy, specific volume, specific kinetic energy, specific potential energy are also intensive because they don't depend, they are not additive. If I have molar mass of two identical systems, when you put them together will not double, obviously, but extensive property means they will double. Okay, so to summarize, we have described a system with different kind of properties, and we'll call the collection of all these properties as a state. So if I describe a system by state 1, and later on I say the system went to state 2, then we will describe the properties of state 1 by a bunch of properties like P1, T1, V1, U1, H1, S1, you name it, capital E1, capital E1. We can go on and on. You get the idea. Similarly, for state 2, it will be P2, T2, V2, etc., etc. So to describe a system, we need a bunch of properties, different kinds of properties. And so far, we have just talked about two kinds of properties. All these properties can be divided into either extensive properties or intensive properties. And we also have defined what is specific properties, recall that. So just to improve on our division we just now did, properties can be extensive, and extensive properties, when you divide by mass, become specific property. And specific properties, and the other kind is called intensive. All the specific properties are also intensive properties. So this is just a little subtlety here. So all properties can be extensive or intensive. When you divide by the mass m, we call them specific properties. And some properties are intensive fundamentally, like pressure and temperature. You don't have to divide by mass. But say extensive properties, capital U is an extensive property. But if I divide by mass, it becomes small u. And small u is an intensive property. Well, this kind of states are called system state. We will discuss another type of state before we go and solve some problem involving these concepts. So I'll stop here so that you can go over what I have done with this description of a system state, and we'll translate these concepts for a flow in the next section.